So hello everyone, now we are in the final video of our PyTorch series, and it's the most exciting part. In this video we're actually going to train a deep learning model. So all the learnings from the previous videos about tensors, about data loaders and data sets, we're going to use it in this video. So in the previous video we used and we loaded the Stanford open source dataset, loaded it using the custom dataset loader that we wrote, right? In this video we're going to actually train a deep learning model in order to classify the dog images from that dataset. Now the catch here is we're not going to train a deep learning model from scratch. We're not going to do that. We're going to use a CNN model, right? So it's a classification problem, and we'll be using some pre-trained model, for example ResNet 18 or ResNet 50, and we're gonna do something known as transfer learning. Now what is transfer learning? In transfer learning we actually take the learnings of a particular model and try to adapt it to another different problem statement, but the catch here is that the data should be from the same distribution, right? Given that these pre-trained models have been trained on very huge data sets such as ImageNet, which contain around like 1.2 million images with around 1,000 classes, the features learned by these by these models, the CNN models, can be adapted into our problem statement also, because our images are dogs, right, which have very similar distribution to the ImageNet dataset. So that's what we're going to do. There's another concept of fine-tuning. So the difference between transfer learning and fine-tuning is that in transfer learning we don't want to tamper with the weights, right? So we don't want to tamper with what the CNN model has already learned, the features. So we freeze everything. So we freeze the learnable parameters. Learnable parameters are the parameters which comes as part of the CNN, the convolutional neural network layers, the max pooling layers, right? So we freeze all of them. Those won't be tampered with during the training task. We only keep the last layer intact, or we replace the last layer with something more trainable. For example, if the last layer is a fully connected layer, linear layer containing 1,000 classes, for the ImageNet, in our case it would just have 150 classes, right? So that is the last layer which is trainable, and everything else is frozen, because CNN actually works like a feature predictor, right? Or it's like a feature extractor. So all the CNN layers actually extracts the features, and the last layer does the prediction, the fully connected followed by a softmax. So we're going to do that. We're not going to touch the learnable parameters and just replace the last layer in order to do the transfer learning. Now when it comes to fine-tuning is a bit different, where we have a trained model on our data set and we are trying to improve the model by adding more data to the data set, right? So let's say I have dogs, I have 150 classes, and every class contains around 100 images, 100 to 150 images, and I train a model. Let's say get around 80 to 85% precision on it. Now let's say I get new data for each of the classes. So I'm going to take the trained model and then again fine tune on the new data, right? And so there are a few thumb rules for that, where you like reduce the learning rate because you don't want too many drastic changes in your parameters. So that's fine tuning, where we do it on the same data itself using the trained model that we have already. But in transfer learning we actually take a pre-trained model and try to adapt it to the problem statement at hand. So that was the difference between fine-tuning and transfer learning. Now let's get on with this video, because I think it's going to be extremely exciting for guys who are training deep learning models for the first time on a custom data set, and even for people who have been training deep learning models. I guess if you're coming into PyTorch, this is going to be helpful for you. So let's get on with it. So in the previous video we went over the train and val data loaders. We saw how we can load batches of data during a training step, and we also got the items and labels. So in this video we're going to focus more into model creation and model training. Primarily we would be looking into how we can take a deep learning model and train over all the data points that we have. The first step would be to get the number of classes, of course, and we can easily do that by taking our train data frame that we have, and we can just take the length of the converted labels column. So that gives us the total number of classes, which is 119 in our case. So there was a short typo there, just fixed it quickly. Now the next step would be to load the model, and I would actually be taking a ResNet 18 model for this case. Now I would set the device for our training. Basically in PyTorch, when you train, we have to set the device on which we cast our inputs, labels and models to. So we would set it to GPU, and the label for that is CUDA 0, which basically defines the GPU device ID, right? So if you have like 2 GPUs, you can also do CUDA 1. That's the GPU you want to choose. Otherwise, it's basically CPU. So we can use torch.cuda is available in order to do that. The next step is to get our deep learning model. So we wouldn't go and write a deep learning architecture from scratch for this use case. We would basically be choosing a model which is provided by PyTorch model zoo. So here we are taking ResNet 18, and we are going to like put down the flag which is pre-trained is equal to true. This will actually download all the weights. Oops, there seems to be an error. Okay, I got it. It should not have a underscore actually in pre-trained. So yeah, so now what it did was it downloaded the model weights, and as you can see, this is the summary of the entire model. It has been trained on ImageNet, which had like 1000 classes. That is why we have like out features is equal to 1000. But for our use case, we will set it to 119, which is the number of classes. So a quick intro on the ResNet 18 model. Here we are on the official Torch Vision models page, and we have ResNet 18 over here. As you can see, it provides the ResNet 18 pre-trained weights, which are easily downloadable, and we just need to set pre-trained is equal to true. Here it's mentioned that this has been reproduced by training on the ImageNet model or the ImageNet dataset, and it accepts PIL images of this form, which is the batch, channel, height and width. And as you can see, the normalized values are also given, right? And these are the same normalization values which we are using in our data loaders as well. So now you get the point, right? Like, why did we choose these values? Because this is actually the standard deviation and mean values of the ImageNet dataset. Cool. So now the idea is to update the out features value in the ResNet model, and we'll only be fine-tuning the model, which means we'll only be fine-tuning the last layer of the model. We don't want to change the weights of the convolutional layers, because our dataset is pretty similar to the ImageNet dataset, and we want the weights to be same. And fine-tuning the last layer by freezing all the other layers actually works. So here you can see that the number of in features of this linear layer, which is marked as FC, is 512, right? Because we took number of features as model.fc.in features. Now we're going to update this layer by setting the number of out features as 119, which is our number of classes. So let's go ahead and do that. So we'll do a model.fc is equal to nn.linear, and we'll also pass the number of features, which is the number of in features, and we will pass the out features as the number of classes that we had, which is 119. As a result, the final linear layer of this model would be converted, and now would be having the output features as 119, right? So that is what we wanted actually. The next step would also be to cast this model to the device that we defined earlier. So we're just going to go and do a model.to device, which will make sure that all computation happens on the CPU, right? Now two of the most essential components of a training activity along with the model would be the loss, of course, and the optimizers. So let's go ahead and define our loss. So we'll name it as criterion loss, and we'll be choosing cross entropy loss for our use case, because we'd want the probabilities scores to be calculated per class which is present. We wouldn't be using a softmax layer, which is done when we have like categorical variables, but here we just have numerical numbers, right? So we just want the model to give out that particular number. That's it. Or what it would do is basically like give a probability score corresponding to that number, and we'll be choosing the max of it. For optimizers, we're taking stochastic gradient descent. So optimizer is an algorithm which tells the entire pipeline how the weights should be updated, right? So that is what the optimizer does over here. We've also mentioned the learning rate and the momentum. So the learning rate is basically how quickly the weight update happens, or it's kind of an offset to the entire weight update function. And momentum is a special parameter in the stochastic gradient descent algorithm, which makes sure that if a particular weight value is actually stuck at a local minima, it makes sure that it pushes it out of that local minima. So momentum is kind of an added boost to the algorithm. It's again a scalar value which is used to update the weight parameters, and it prevents it from getting stuck in a local minima, right? So yeah, we'll go into details of loss functions and optimizers later in for like other videos. For this purpose, for this video's purpose, let's keep it simple. We just have a cross entropy loss to get probability values for the classes that we have, and then optimizer to update the weights. So if I have to give you slight details about the optimizers, right? So basically, what is an optimizer? The most common form of optimization is the gradient descent algorithm, where first the loss function is taken and the gradient is calculated. The gradient is calculated, why? Because we want to minimize the loss function, right? And then we do an optimization step where we update the current so the new weight values become the current weight values minus the learning rate multiplied by the gradient value. So that is the standard gradient descent. What is stochastic gradient descent? It's an update on the standard gradient descent. In a standard gradient descent, the update would happen after the entire data set is trained once, but in stochastic gradient descent, it does it multiple times. So it's kind of an update, and it makes sure that the so when it is being done multiple times, so the convergence is faster, right? So it is kind of pacens up the entire process of reducing the loss value and taking the weight to the appropriate number, right? Momentum, as I mentioned, tries to push it out of some areas in the entire gradient slope. So the entire the weight value might get stuck in something known as a local minima, and there might be multiple oscillations happening in and around that point. So the momentum actually helps it push it out of those spots, tough spots, and reduces the oscillations and tries to make sure that the gradient is actually moving in the correct direction. Now that we know about the optimizers and losses, let's go ahead and define a few dictionaries which will hold some important values. And these values are, of course, the train and val data loaders. We would be referring to them quite frequently, so the best thing to do would be to store them as dictionary values, and this would actually like reduce the lookup time a lot, and we won't actually have to remember much variable names. We can just store them as key value pairs, right? We can also take the dataset sizes as part of a dictionary itself. We won't have to do a length of dataset, train dataset or val dataset every time. So this will save up a lot of lookup time. So we're doing that. We have a data loaders dictionary and we have a data sizes dictionary. So yeah, so that's data loaders, and we have a train and val keys and the corresponding data loaders to that. And then we have dataset sizes. So we have the train size, which is 16464, and the val size, which is 3292. Now, this is the main step where we go ahead and define our training function, right? And in this training function, which we will have all the steps of like doing the forward pass, doing the backward pass, everything. So the parameters to this function would be the model, the criterion, the loss, it's of course the optimizer, and the number of epochs. The number of epochs, we have mentioned it to be 10 as the default number of values. Just feel that 10 is a good number for the experiment. We also want to log down the time it took for the entire process to run. So I will define a variable called start time, and we'll be importing the time library for that. And if we just do a time.time, it would like log the current timestamp. Let's quickly go ahead and put down some other utilities in this function. So the first one would be the best accuracy variable. So this is the variable that we would be constantly updating throughout our entire iteration, right? So whenever we get an accuracy which is better than the previous one, we store it as best accuracy. Now, how would this entire function be laid out? We would have one loop which will go over all the epochs, right? So for here we have the variable called number of epochs. So we'll have a loop which will do like iterations for those number of epochs. We would want our data set to go through the model that many number of times. Now, the next loop would actually go over all the data points, once through the train data loader and once through the val data loader. So the validation would happen at every epoch. So once all the data points in the data set pass through the function, the weights are updated and the optimization is being done, we would take that model and we would run the model. We'll run our validation data set through the model. So another loop is to choose between the train and val keys. So the first would be if phase is equal to train, we would set the model to the training mode, where it would make sure that the gradients are updated. And then if not, so basically if it is a validation step, we would set it as model.eval, so nothing would be updated, right? So basically all the gradients in the model won't be updated. It will just do a forward pass and get the values out. So now let me go ahead and put down the other loop that I spoke about, where we would iterate over the entire data loaders, the train data loader for training and the val data loader for evaluating the model once the training is done for a single epoch. Let's quickly go ahead and do that. The last step, you can see I've defined the epoch loss, which is the running loss divided by the size of the data set, and then we have the epoch accuracy as well. So running loss and running corrects. Running loss contains the losses, the sum of losses for that particular epoch, right? And running corrects contains the sum of correct values for that particular epoch. So we keep adding it for every epoch that we have, and at the end the epoch loss would be the running loss divided by the dataset size. That would give us the epoch loss, right? And then we do the same for the epoch accuracy as well. So it's kind of, epoch loss is kind of an average. So running loss, which is basically the loss for, actually it is not all the epochs, it's all for all the batches. So we take the running loss for all the batches and we divide it by the size of that particular phase, which is train or val, and that gives us the epoch loss. And similarly we do it for epoch accuracy as well. So we like collate the losses for all the batches and divide it by the total number of batches in order to get the average value. At the last step, we check if the phase is val and if the accuracy is better than the best accuracy. Initially that value is 0, so we just copy that model to something known as best model weights, and we also actually put down the training time. So we do a time.time minus start time, which was initialized at the beginning of the function, and we put it down as training completed. And so that this function, guys, is the complete function for training our deep learning model. Now this function is actually an example from the PyTorch documentation itself. Finally, we print the best validation accuracy, right? Which is basically the best accuracy corresponding to the best model weight, and then we just load the best model weight using model.load state date and return it back as the return value of the function. Cool. So now is the time to like execute a function and actually run it. As you can see, the current phase is train. We have passed the model that we loaded, the loss function, the optimizer, and we have set the number of epochs to 25. And we have like 515 batches, and the batch size is 32. So those are the number of batches. And it's a small tweak that I did to the function. You guys can find it on GitHub. I just added a TQDM loader to the iterator, to that loop where we load data points from the data loader, right? So since this example is being done on my laptop, which has a CPU, so I won't be able to show you all the accuracies for the epochs. Let's quickly head over to the Google Colab page where I actually did my training. Google Colab is an extremely beneficial platform to train deep learning models for free on GPUs. So I just used that, and let's quickly check that out. So this is the Google Colab page. As you can see, I have the same function over here, which is basically taking in the model, the criteria, and the optimizer. I have an extra variable called scheduler, but I'm not using it over here. We'll go over schedulers in like other videos, but rest of it is pretty much the same loop where I go over train and val,
and then the data loaders, and the running loss, the running corrects, and yep. So I've trained it for 30 epochs, and as you can see, after 30 epochs, the train and val accuracy is not that bad. And we have a val loss of 0.45 and a val accuracy of 0.85. So the model is converging to something. Cool. I will also link this collab in my GitHub repo, and actually I'll have the entire notebook in the repo. So I guess that should help. Let's get back to our video.
So we're done with our model training, and this is the final video in this PyTorch series. I hope you guys got to learn from it. We learned a lot about tensors, about data loaders, data sets, and how to train a custom deep learning model on a custom data set. So I guess now you guys can go ahead and experiment with new deep learning models and like train from scratch if you want to on custom data sets. In order to train from scratch, you just need to not set every layer as frozen. You can just unfreeze all of them and train it. That would train a deep neural network from scratch, and you guys can go ahead and try it out. You can experiment with a lot of other things, actually play around with the hyperparameters, the learning rate, etc. We'll be doing other videos also on detailed PyTorch training, detailed deep learning training, where we'll play around with hyperparameters, and that specific thing is actually known as hyperparameter tuning, where we like go over a set of hyperparameters and train our deep learning model. So we'll have those videos in the future, but I hope you got to learn a lot from this series. The link to GitHub for all the codes, the notebooks, and as well as the collab link would be down in the description below. And if you liked this series, please press a like button and hit on subscribe. It would mean a lot for the channel, and since I'm new to YouTube, and this is a new channel entirely, a like and a subscribe would actually boost the entire channel forward. So looking forward to making more videos in this new year and growing with all of you. Thank you everyone. See you in the next video. This is me, Abhishek Bose, signing off.